Morning, guys. So this is just a continuation of our review on electron configuration as a model. We saw how the Bohr model itself had some limitations, and we've been trying to, with new evidence, we've been trying to modify our understanding again of the atom. So today I'm just going to recap with you a little bit of electron configuration. The new part here will be when the atoms themselves start becoming ions, positive or negative. There are a few extra rules for us to follow. So we're going to be referring back to the data booklet. I've just captured an image of the periodic table. So this is section 6. Remember, on your periodic tables, this is what's shown on your blue table so far. On this table, unfortunately, because the font is fairly small, you're not actually given the element names below every single symbol itself. But if you've seen the data booklet, you actually realize in section 5, they have an alphabetized listing of the element name as words. So say like beryllium, it'll say right beside it, the symbol is Be, and it'll just tell you what the atomic number is. So if you really are at a loss at which element is which, you can definitely look in section 5, but hopefully the most familiar which you'll be able to recognize. So as we mentioned yesterday, electrons enter these different orbitals, the different floors on the hotel, the different types of rooms, but they always go in the lowest energy first. That's sort of like the Bohr model, where the electrons are always entering the lowest shell, and we refer to that as the ground state. We've tentatively separated our periodic table into 4 segments. So we're going to separate our first 2 columns, and we're going to try to keep this clear so you can see it later on. But we're going to separate the first column. We'll call these S block. So electrons that enter those ones are going to be in S orbitals, S kind of rooms. We're going to have the latter 6 columns here. Row 2 starting onwards to row 6. This one here is called P block. So electrons entering those ones are going to be P electrons. We don't actually get into the Ds until we get to our transition metals. So here we have transition metals. These ones here are D block. In chapter 3, we're going to come back and actually take a look closer at transition metals. But for the time being, we're just going to fill in their orbital designation. And then for F block, if you just take a look at the element number, specifically looking at row number 6, for example here, these 2 electrons, cesium's electron would be the first electron in. Row 6, it's S block. Cesium's electron would have been a 6s1. When you go over to barium, remember Pauli says every room, say this is a 6s room, cesium already had the first electron go in, barium is actually going to be the second electron, this would be a 6s2. Remember, the placement on the periodic table actually tells you which electron each element is going to gain. Every element, the energy spacings might be different because that depends on the number of protons, but at least the relative ordering of which room comes next, what's the next highest energy reading is always going to be the same. For this latter part here, it's going to get a little bit strange. We talked about here that D's are already a little bit weird. Back when we went to the 4 S's here, we saw that by the time energy shell 4 had split, 4s actually ended up lower energy than 3D. So by the time row D shows up, even though technically we are row 4, what I was asking you yesterday was, remember that the D's actually come in 1 row shorter, and this is actually 3D. Whenever the D rooms actually show up, they always show up as 5 rooms. We do our bus mentality as we go through our Hans rule. We're going to go 3D1, 3D2, 3D3, 3D4, 3D5. We all take our own seat unless there's already singly occupied. So for example, scandium 1 would be the first guy in, 3D1, titanium here, 3D2, and so on and so forth, all the way over to 3D10 before you enter your 4Ps. So looking at our periodic table, and this is how we're going to predict it, we went through element 56, which was for barium. Element 57 is lanthanum. This is technically a D block element. Where row 3, row 4, row 5 for the D blocks, this is going to be your first electron into lanthanum. So this one here is going to be 5D1. What you'll notice here is hafnium, which I asked you for yesterday. Hafnium should have a 5D2. But if you take a look at the element number has skipped from element 57 all the way to element 72. So suddenly we've lost 14 electrons somewhere. Where those electrons actually went, if you just track the element number, we actually pulled out what's referred to now as the F block. Element 58 is actually down here. So it's sort of like going from lanthanum. Lanthanum had picked up its 5D1. We jump over to cerium. Cerium here is going to be our final block here. This block here is going to be called F block. And I told you for the F blocks, when these show up, these actually show up eventually starting at 4F. This one here is going to be 5F. So what's happening here is for lanthanum, we would have picked up the first D electron, But by the time you get up to the really top parts of those energy level diagrams, the energy spacings between, say, 5D, I know the Ds always come as 5 rooms, and then the 4Fs, by the time they actually end up splitting, they're so close in energy that we have picked up, say, lanthanum here has a 5D1. It actually, before we come back for 5D2, we actually start going to cerium. Cerium is the first electron into 4F. We're going to start filling in 4F1, 4F2, 4F3, 4F4, going all the way across. We need to completely fill. Every time the F room shows up, we have 7 orbitals. Again, Pauli says every orbital is a room, and every room can hold 2 electrons per room. So by the time we go 1, 5, 6, 7 here, we're going to double back on ourselves, and we're going to go 4F8, 4F9, 4F10, that's going to be 4F8, 9, 10, all the way through to 14. So, this last part here is a little bit strange. Let's imagine I was just doing hafnium with you again, and then we'll practice a few more here. So hafnium, you would see hafnium actually has a lot of electrons. Hafnium is the element that's sitting here. You can predict, based on the periodic table, what the very last electron should be. We had already decided it's on row 5D, it's the second electron in. But because what we're doing is a full electron configuration, we need a full roster of which electrons, where do the electrons go in each of the hotels. So what we're having to do here is for a full configuration, I know I want to end at element 72, but I need to go right back to hydrogen. Remember, for this memory aid here, it's like helium is here as well. I want to start from hydrogen and build all the way up until I have all 72 that's tracked. So here's how this looks. We're going to start off with hydrogen and heliums. Remember, we're row 1, we're S block. Hydrogen and helium, this one would have been 1s1. Helium would have been 1s2. Hafnium definitely has both of the electrons. We just track the total room here. Hafnium here has 1s2. The next electrons that go in, electron number 3 that lithium has and beryllium has here, we're now row 2, S block. This is going to be now a 2s1 and a 2s2. So in that case there, again, we just track the full shell. Yep, hafnium at least has 4 electrons, 2 in the first shell, 2 in the next shell. I'm just going to sketch this part for you here. I'm not going to draw the whole energy level diagram. So far what we've been doing is hafniums, again, its energy spacing would be different from other elements, but at least so far, hydrogen's electrons, helium's electron, lithium, and beryllium's electron. So far we have those full, and we just track the full number. As we step over, where does electron number 5 go? We're now row number 2. This is called period number 2. The S's and the P's follow it really nicely. Boron is the first electron in. This is 2p1. So that's going to be the first electron into the room. We're going to be blowing right through this 2p1, 2p2, 2p3. We're going to double back on ourselves, 2p2, 2p3, 4, 5, 6, because hafnium definitely has more than these 6 electrons. So let's continue here. We have 2s2. I'm telling you that the 2p's are full, so let's go 2p6. Where do the next electrons go? We've just gone by neon. The next one here is going to now be row number 3, again S block, completely full. We're going to have a 3s2 by the time we get to magnesium. Electron number 13 for aluminum, which we practiced yesterday, 13 through 18, row number 3 P block. This one would have been a 3p1 all the way up to 3p6. Because hafnium has all of those electrons completely full, I'm just going to track the full number here, at least all the 3p6s are full. I would recommend to you just continuing following the periodic table. For example here, by the time we have 3p6, we know we have a 3D row that's coming up, but remember, by the time the energy shell 4s had split, 4s actually ended up lower energy than 3ds. So because we off-ball, because we build up lowest energy first, potassium's electron would be 4s1, over to calcium, which is 4s2. Again, that's full, 4s2. Technically, this is energy level 4, but remember, by the time the energy shells have split, the 4s had ended up a little bit lower energy in 3D. We're going to come back to that reality in chapter 3 to describe why transition metals are actually multivalent, but for the time being, we just off-ball. We had completely filled up the 4s before we start filling in the 3ds. So for potassium and calcium, we had 4s1, 4s2. First time a transition metal show up with scandium, we said they show up 1 row shorter, which is 3D. Scandium would have been the first electron in, so it would have been this 3D1 as an example here. It's okay to put the 3D afterwards because that's actually higher energy. And as we step over, it's going to be 3D1 all the way to 3D5, then we double back on ourselves 3D6 all the way to 3D10. Again, hafnium have those completely full, so I'm just going to track the 3D10. At this point here, IB likes to put all energy shell 3 together. So, for example, for this latter part here, you might sometimes see this written 3s2, 3p6. So I'll actually write down the 3d10 first, and then for s2, what I want to emphasize here is the left and right order does not matter. As we step across here, we would have still gone 4s1, 4s2. I would have no d electrons yet. I would have picked up scandiums, 3d1, 3d2, 3d3, all the way at this point here to 3d10. I'm still adding them in the order that 4s went in first, by at least the left right order. And like we'll see very shortly here is this is where energy level 3, when we say you can have 8 electrons or 18 electrons, it would be 8 electrons. If you look at the S and P electrons, these are referred to as your valence electrons, because these ones here are the ones that are furthest out. These are the ones that the board won't actually track. By the time we get into these d orbitals, as we'll see tomorrow a little bit during the shapes here, there are 10 electrons that do belong to shell number 3, but those d electrons are held really tightly to the nucleus, and these ones don't behave in the same way that your valence electrons do. So if you add those 10 electrons, in total 8 plus those 10 would end up giving 18, which is why in the context that we have, it would either be 8 or 18. I keep digressing here. Let's just finish off this hafnium electron here. We have 3d10. Once you pass 3d10, we're on row 4 again. 4p1 all the way to 4p6. Just tell me it's full. So we have 4p6. Moving on then, we have rubidium and strontium. This would be 5s1, 5s2. Again, completely full by the time you get to the strontium there. So 5s2. We get our second row of transition metals, no problem. So we have 4d1 all the way up to 4d10. You see how the periodic table actually gives you a nice hinting of which is the electron that comes up next. I'm just showing you all the shells being full. And then by the time we get to here, 5p1, as you would add it across, xenon now has 5p6, so 5p6. And finally, we get to the most interesting row here, which is this latter part. I'm going to do this part here in a little more detail. So cesium's electron would be 6s1, 6s2. Hafnium is beyond that, so hafnium again has a full 6s2, no problem. 6s2. Based on the way our periodic table is arranged here, we do pick up our first d electron. So this is row 5, the first d electron into it. This one here would now be 5d1. Normally, by the time you get to 5d1, normally you say, okay, let's fill up all the 5ds before you continue on filling the 4s. This part's the weird part. I picked up the 5d1, but I don't get to come back for 5d2 until I've jumped over to the F block. So it's like going from lanthanum, going to cerium, which is 4f1, going through all 4f14, and then coming back to 5d2. So because I've gone through all the F blocks here, I'm going to call this 4f14. When the F blocks end up showing up, they show us 7 rooms, they max out at 14 electrons total. And then finally, once we're completely done this is completely full, now we're allowed to go back to hafnium. Hafnium is a 5d2, just a way of tracking it here. You could write 5d2 like this, but that part there gets a little confusing. Well, do I have 1d electron, or is it cumulative, is it 3? Remember, the left and right order doesn't matter. You could have come along, instead of putting it as a separate entry grid, you could have changed this one here finally to 5d2. Remember, the notion here is the left and right order doesn't matter. I see that all the F blocks are completely full, and now we're just starting to finish off the D block. So either you do the 5d2 on the left-hand side, or you can have the 5d2. Oh, now since we're filling in the rest of the 5d2s, we can have the 5d2s here. So that is the electron configuration for hafnium. If I add up all these superscripts here, these above numbers here, this should give me hafnium's element number, which is 72. 72 protons means 72 electrons, and here's a full roster. Consistent with the Bohr model here, we said shell 1 is only supposed to max out at 2, max out at 8 for shell 2, shell 3, 8 or 18 like we just saw. First 2 electrons, shell 1, closes that shell. 8 electrons closes the second shell, perfect. We just talked about the 8 and 18 for the 3D. The 4s, if I look at all the energy level 4s, you're going to likewise see it's either 8, if you're looking at S&Ps. Those are the 4s2 and 4p6, so that's going to be 8. If you then consider, well, what about the d electron of shell number 4? You could have said 18, if you include all 3 of those. And even worse, because energy level 4 actually has these 14, you could even say, if you combine all 4 of these numbers here, this number here would actually be 32. Again, d electrons and f electrons behave a little bit differently than the s and p electrons, so Usually we just say 2, 8, 8, 8, and we just keep going down. The Bohr model really breaks down by the time we get to calcium, because it really doesn't do a good job of plotting the electrons. Tomorrow when we come back to take a look at the orbital shapes, we're going to have a little bit more understanding of what makes these orbitals different, why are only the S and P's called valence, and then we'll come back to what the D's and F's are here. So, you see that that's a lot, because this one here is called a full configuration. I have a full roster of what's happening here. They will be asking you for full configuration. Really, they're only going to ask you full configuration up to this 4p6 for what is that? Is it krypton? Okay. But I'm just showing you more details so you can do the big ones. If I'm just interested in the valence shell, if I'm just interested in, well, for the Bohr model, I don't care how many inner shells come along for the ride, because it's only this outer shell that actually matters anyways, we can switch from a full configuration. This is going to become a shortcut for us. We're going to switch to something called core notation. Core notation, or either a simple electron configuration. In the lesson, I think 2 days ago, I mentioned the term electron arrangement, where we were saying, well, 2 electrons, 8 electrons, 8 electrons, something like that. Okay. In this case here, the simple configuration using core notation actually is a shortcut for this configuration notation. And it does exactly this, where I'm going to ignore, or I'm going to hide all the core electrons, and I'm just going to show you the detail of the valence electrons, the outermost shell. And how we're going to do this is we're going to have a notation to actually hide the core. The core, having full shells, actually marks off noble gas. Helium has a full first shell, neon has a full second shell. We're going to see which noble gas hides all the inner shells for us, and I'm just going to leave the remainder on the final shell, and that's going to tell me something about the valence. So if you look at where the noble gases are, with the exception of helium, which ends off here with the 1s2, that closes the first shell. First shell is tiny and can hold 2. The other noble gases here, row 2, 2p6, 3p6, 4p6, p6 will actually be a hint that the shell has ended. So if I go through this half-game configuration, aside from the 1s2 that closes the first shell, and it is 1, n equals 2 here would be a 2p6, 3p6 closes the third shell, 4p6 closes the fourth shell, fifth shell 5p6. Hafnium has 5 full inner shells and just a little bit more than it. I'm going to hide the 5 inner shells using the 5th noble gas. So we have helium all the way down, we have xenon as our noble gas. We're just going to use square brackets for xenon. Xenon actually hides all of these electrons here, 5 full shells. And we're going to say hafnium is basically xenon's configuration, but we're just going to leave off this last shell here. It would be xenon plus the 6s2. We had filled in, say, 5d1. We started filling in 4f1, 2, 3, 4, all the way up to 14. And then now hafnium has come back, and now it's a 5d2. Again, the left-right order doesn't matter. You could write xenon 4f14, then 5d2, then 6s2. The order just matters how you actually put them in. So that's how we do core notation. You will be asked for both. Because full configuration gets to be very long, they're going to typically ask full configuration for the earlier elements. You're not having to write a lot. By the time we now have core notation, you're actually able to write some of these bottom ones. So hopefully that helps you flesh out a little bit of the electron configuration stuff. On your worksheet, you'll have a little bit more practice. There's a few last things I want to do with you for this lesson. So we just practiced through full configuration, core notation. The 2 last things I want to do with you is there are some exceptions for you to track, especially by the time we get down here. Why is it 5d1 is picked up the first one and I don't actually get to 5d2? Energy levels are really close together. Definitely a lot of exceptions toward this bottom that we're going to see. But the 2 exceptions that they want you to know are specific to, let's just look back here, are specific to chromium and the elements underneath it, and copper and the elements underneath it. So just as exceptions, just for you to practice, take a second. See if you can write for me, right? The full electron configuration. What would you have said based on what we know? Write the full configuration for, let's do copper first. And just for simplicity here, use the core notation. Again, they're going to ask you both. They're going to ask you for the shortcut notation. What would the shortcut notation look like for, say, chromium? Okay, you can pause it, you can try it out for yourself. You won't get that summary table I gave you yesterday, but you will have the periodic table. You can just trace your way through. So let's have a look here. Copper, I'm going to look at where it is. So copper is in my transition metals. It's the first row that the D blocks show up. We had set this is energy level 3. Copper is the 9th element here. So we go 3D1 all the way through to 3D9. Based on what you said so far, if I can just trace it down really quickly here, 1s2, 2s2, 3p6, 3s2, 3p6, 4s2. This is what we would have said. Again, if you want to compare copper and chromium on the same column, they're going to have the same inner shells. S2 closes the shell, P6, P6. That says copper and chromium have 3 full shells, that 288 that we've been talking about. That's the electron arrangement. The noble gas that has 3 full shells is the, can't really see it here, this one here is, I think, argon. So we have argon. I'm going to actually use square bracket argon to hide all of these 18 electrons. And chromium, similarly, is in 3D. It is only the 4th element in, so 3D1, 2, 3, 4. Based on what we have so far, we would have said chromium, 4s2, 3D. These two are exceptions, so you want you to be really careful with them. Okay, these are the two that I want you to memorize as exceptions. These don't follow the rule. And the exception actually comes in, this is, again, because the 4s and the 3D for each of these elements, because they're so close, if we're on energy level diagram, because they're so close in energy, so far we have this picture. 4s2, 3d9 would have been a d1, d2, 3, 4, 5. Again, convention sake, we just put in the up arrows first. Because these are so close in energy, what's going to happen to copper, and we'll see again for chromium, we're going to see that out of the 10 spots we could have filled in for the d electrons, we're just 1 missing. I have 9 out of the 10. If only I could get 1 more electron. One way to do it is it can pick up a charge. In this case here, copper says, wait a second, I do have other electrons. It is going to cost me a little bit to actually promote this electron up, like we saw in the absorption lab from earlier. I'm going to pay a little bit to promote my s electron up to this shell, and at least that ends up filling in the 3D shell for me. In that case there, I know we're not fully a noble gas. Noble gas should have been a 4p6, but for some reason here, we know that somehow a full shell adds stability. It makes this element here able to relax a little bit more because it's completely packed. Just like noble gases are stable once I have all the electrons paired up and a complete shell. In this case here, we're looking at those inner d electrons. Well, I already had 9 out of the 10. If I can promote, instead of 4s2, if I promote one of those electrons up, let's make this actually a 3d10, and let's leave it as a 4s1. This will give me some full shell stability. So this is what copper ends up doing. We have a 4s1 and a 3d10 because one of those electrons can be promoted up. And that's because these are close enough in energy, even though I am having to pay a little bit. Let's say give me $10 and I can move this electron up. I don't really want to do that. But what if I guarantee you, by the time you give me $10, I'm going to give you $100 back. So you had to pay a little bit up front, but the amount of stability that we get more than pays you back for what you put in, so copper would definitely do this. For chromium, very similarly, it's looking at the 4s3d. Again, the energy spacings might be a little bit different because of the number of protons, but in this case here, chromium would have had a 4s as well as 3d. Chromium has less electrons, so far we have a 4s2 and only 4 of the electrons in the d shell. We're nowhere near a full shell, but in a similar manner, I have 5 d rooms on this floor. If I can pay a little bit, give me $20 and I'm going to move that up, and I give you $500 back, of course, why wouldn't I? So in this case here, full shells add stability. Even for chromium, half-filled shell adds stability. Whenever you see these two elements, be really careful. Although we would have said 4s2, 3d4, we're actually going to write it here, 4s1, 3d5. That's just plain old copper and plain old chromium as an exception. As we step over to charges very shortly here, we're going to start off with this and then do the rules for charges. So these are the two exceptions. Does this apply for anything else? These exact exceptions would apply for the elements directly beneath it. Because if you think about going from chromium, erase that highlight there. If you go from chromium to molybdenum to tungsten here, molybdenum would have the same configuration as chromium. It's just going to be row 4D instead of 3D. It would have been a 5s2, 4d4. Again, we're going to promote one of the s electrons up. 5s1, make it a 4d5. It's going to apply to all the elements underneath. Copper, silver, gold, these ones here would have the same problem. It's just what energy levels that exception is occurring. So these are the two exceptions we want you to know, chromium and copper, as well as the elements underneath. Just watch out for those ones. They could ask you full, as well as fornication. Last thing I want to do with you in this lesson here is deal with configuration for ions. For starters, most of this is going to be fairly similar because we're going to use a periodic table, we're going to be filling in the number of electrons, but just as elements are becoming ions, they either have negative charges, they have more people arrive at the hotel, I need to find a spot for them, or they're going to become positive, they're having lost electrons, I need to pull people that are already in the rooms and actually pull them back up. So let's just go through in order here. Ions. In this case here, typically it's going to be non-metals, but I could actually hypothetically make even metals charged, sodium, sodium negative, and whatnot. But here, non-metals, they typically gain electrons. They grab extra electrons to become, remember the fancy word for negative ion is an anion. This is Richard always like saying, oh, it's like eating onions, very, very negative. Okay? Anion. You are gaining stuff, but the things that you're gaining are negative. The rule when you do this here is, it's like more people arrive at your hotel. Add these electrons, add electrons to the next lowest energy spot, or energy shell. So let's do as just a practice here. Let's do oxygen. I don't really need to specify it as an atom. We would assume that it was neutral to begin with. But let's figure out what happens to oxygen by the time it becomes the oxide negative 2 ion. Oxygen, if you look at your periodic table, has 8 electrons. By itself, it should have already had 8 people in the hotel. We do our energy level diagram. I fill it in. Lowest energy first at off-ball, 1s1, 1s2, 2s1, 2s2. Here's our Hans rule from yesterday. We take our own seat. That's the 8 electrons. And now, when things try bonding, these nonmetals pick up extra electrons. We need to have gained 2 electrons. The fancy language here is it's been reduced. It's picked up 2 electrons. So 2 more people arrive at your hotel. The question is, where do I put them? Well, these electrons are similarly negative. They all also want to be close to the nucleus if they can. The next spot that are available are going to be the 2p5 position, 2p6 position, giving you oxide as 1s2, 2s2. Oxygen would have by itself been 2p4, but now we're going to add those 2 extra ones, and now we're going to get 2p6. What other element has this configuration? 2 electrons in the first shell, 8 electrons in the next shell. We saw it from earlier, P6 usually indicates closed full shell. What's the noble gas in shell number 2? We have this as neon. Yes, oxide is not the same element. O minus 2 ion is not the same as neon, but at least the outward structure, at least where the electrons are and how the electrons are filled, both oxide, if I just go like the Bohr model, both oxide and neon would look the same outward. They're not the same element. We talked about even the radius being different, but at least the outward structure has electron arrangement, 2 on the inside shell, 3 on the outside. The wording we give to these guys here is these ones here are isoelectronic. There's another example of the iso word here. Iso means something is the same. This time oxide, O minus 2, remember it is charged, so put brackets around that. O minus 2 has the same electron configuration, has the same 1s2, 2s2 stuff as the not the same size. We'll come back and check it through the radius. At least outwardly, oxide's done. By the time it's a full shell, these are negatives. Last thing I'm going to do with you for this lesson here, these ones here are negative. What if we're positive? You'd imagine it's fairly simple. Typically, it is going to be metals. Again, not impossible for a non-metal to artificially be ionized and lose electrons. But here we have metals. Metals tend to lose electrons to form cations. Cations and cats are positive features, so cats are positive ions. In this case here, for me to become positive, I need to take electrons that have already entered the room, and I need to pull these electrons back in. As I end up losing these electrons, I end up leaving the atom more and more positive. I'm just going to do, let's say, scandium for practice here. Scandium, take a second, just to plain old electron configuration for scandium. We have 1s2, 2s2, use your periodic table and you can verify this for yourself. Could have been any positive. I want to show you something in this example. So scanning would have looked like this. I can double check over. I put in the 3d1 at the end. If it's 3d1 on my periodic table, we should be 3ds are where the first transition metals show up. Perfect. scandium is just sitting exactly at that 3D1 position. By the time I built up to 3D1, I should have all scandiums 21. There is a special rule for us to losing electrons. There wasn't much of a rule for the anions, you just add them to the next lowest energy spot. In this case here, I'm going to give you the rule as remove electrons, invite electrons back out. They already are in the room, they already have 21 electrons, they're sitting happily. But we're going to pull electrons out. There's a special order for you to memorize, and here it is. Remove the electrons in the order. If you have p electrons, pull them out first, then pull them out s, then pull out the d's, pull out the s. This does have to do a little bit tomorrow with valence electrons. We're going to come back and verify that later on. But this is the ordering that we pull them off. Any p electrons, but like layers of an onion, because the Bohr model actually sort of one layer surrounds another layer, I can't touch any inside shells until the outer shell is done. So there's the order, yeah, p, s, d, f, but here's the rule on the outermost shell. Again, this is where fornication comes in handy, with the exception of helium, which ends as S2. All the other noble gases end with P6, P6. This is telling us that scandium has 3 full electron shells inside. I can't touch any of these electrons until the outer shell is gone. So just focusing on the outer shell, so far for scandium it's the 4s2 and the 3d1. We're going to remove them in this order. It's a little bit strange. If you look at the energy level diagram, we had filled in 4s, our 3d were 5 rooms. So far scandium looked like this. The very last electron that I put in is actually this 3d. But based on this ordering, do I have my 4p's yet? Nope. Do I have s's? Oh yeah, I have s's here. Let's say scandium became scandium plus 2. If I want to invite 2 people back out of the hotel, I don't actually lose 3d1 and then 4s1. Following this rule here, I didn't have my p's yet. I do have s's. I lose the s electron first. So scandium plus would be 4s1. Scandium 2 plus would have completely have a 4s0. And if it's 0, there's no point writing 4s here. Scandium plus 2 would basically be the noble gas with 3 full shells. In this case here, I believe it's argon. It would have had earlier 4s2 and 3d1, but because the 4s2 is gone, it's just left with 3d1. And you'll notice on the energy level diagram, the 3d1 was actually the very last electron I added. This was the highest energy, and yet the electrons that get pulled off are actually the lower 4s electrons that come off first. If I then make it scandium plus 3, again I'm looking at my outer shell. Fornication does a really good job of this. I can't touch any inside shells until the outer shell is gone. Do I have my 4p's yet? Nope. Do I have any more 4s's remaining? Nope. And then I'm going to pull off my d's. So I have a d here, scandium, and then d. Just isoelectronic. So have a look at your worksheet and do some more practice here. I'll give you just 2 just for a trial. See if you can write the full configuration just for practice. Write the full configuration for not as hard as this one here. Let's do aluminum plus 3, and let's do periodic table here. Let's do silver plus, just to get you thinking about the exceptions again. Silver plus, and give you 1 for minus, so let's do P minus 1. Okay, I know that's not phosphorus's normal charge, but just for practice. And let's do arsenic minus 2. Okay, so have a look at that there, and we'll check them